Welcome. This is David Raymond and doing the weekly workshop. So today we're going to talk about networking. So introduction, this is very introductory, introduction to networks. And so there's a couple of weeks slated for network fundamentals. And the reason that's the case, so there's network fundamentals part 1 and part 2. The reason that I ended up breaking network fundamentals into a couple of lessons, we could probably even go into a third discussion, but I pulled out, I've been using primarily the cyber basics content, at least so far, to give these weekly sessions, and I pulled up the introductory networking workshop from the cyber basics content on the website, and that's all content that I put up there last year. You know, it was courseware that was in the repository when we launched, and I realized that my introductory networking lesson wasn't very introductory, and so I took out the Virginia Department of Education competency list for cybersecurity fundamentals, which is 6302 in the Virginia Department of Education CTE curriculum, and decided that I needed to cover more of the introductory networking competencies. So that's the path I've started down today. So this is a whole new slide deck that's not in the courseware repository. It will be in there soon, within a couple of days. I just need to put together a lesson plan that accompanies these slides, and we'll get this stuff uploaded into the courseware repository. So this is a new set of slides you haven't seen before. I just finished them this morning, actually. So, new overview slide for weekly workshop. So coverage of cybersecurity education topics each week, Tuesdays at 1 p.m. recorded. We share them all at our website, https virginiacyberrange.org. So if you click on the community, big community button on our homepage, there's half a dozen or so recorded workshops by me and some others in the Virginia Cyber Range office, and we will continue going at this weekly pace. Probably not forever, but for a long time, because we got a lot of things we can talk about, and I think hopefully it's all helpful for folks who are teaching these concepts in the classroom. And if you have a particular topic that you'd like to see, please feel free to send us an email. You can email me directly, or you can send a note to the contact@virginiacyberrange.org email address, and we will put your requested topic in the queue. And I'm gonna pause just for a second. I want to look at the chat window. I'm assuming that. Oh yeah, you're welcome. So I want to check the chat because I'm doing this a little bit different today. I'm not in my office. I'm in a different place, and so I can't see my chat if I want to see my slides at the same time. So apparently everybody can hear me, which is definitely good news. I apologize if the quality is not great. I'm on a hotel Wi-Fi and seems to be working okay, but I'm sure Maureen will call me on my cell phone if something goes awry, because again, I'm not looking at the chat. Okay, so a couple of interesting recent news stories, and these are things I just pulled off the news this morning. First one: hackers targeting election networks across the country prior to midterms. And so this is probably not particularly surprising that there are reports of election networks being targeted, and we think that those election networks have been targeted by lots of it by foreign nation state adversaries or people who just want to, some of it might be motivated by foreign nation states who want to cause U.S. trust in their election system to be degraded, right? So if they can do malicious things to our voting systems, then people lose trust in that whole process, and that's bad for the U.S., right? It would be bad for anybody, I would imagine. Any country that holds sort of free and open elections, it would be bad if people lost trust in that whole infrastructure. So there's certainly motivation for foreign adversaries to do malicious things. There may be motivation for people within the U.S. to do this kind of thing, and there was a accusation. I'm not going to delve into it, but there was an accusation a couple of days ago of one party in a particular state attempting to hack the network of the other parties. It was a state convention, and this potential attacks on voting systems are not new. There's been a lot of talk. You hear things kind of regularly. At least I do. I don't know. Maybe just because of the websites that I frequent, but you hear of vulnerabilities in voting booths, right? So there are now these electronic voting booths, and they've sort of gone in and out of fashion in different states because there's a bunch of them released 10 or 15 years ago, and it was this, everything was being turned into electronic devices, and so why should we fill in circles on paper when we can vote using a computer? And so there were these electronic voting booths that were created, and then there were vulnerabilities discovered in the individual voting booths, and then so that use of those things was scaled back, and it sort of comes and goes in different states. And so you hear talk often of voting, the actual physical voting mechanism being manipulated, or the potential for manipulation, right? And I think there's a certain amount of bait and switch there, right? If you focus people on the physical voting systems, which seem to be poorly secured, you sort of lose sight of the fact that that's really not in most cases that's really not a relevant threat vector, right? So in order to manipulate those voting booths, they're virtually none of them are connected to the internet, right? So they're all isolated standalone systems, or maybe a small network in the voting center where these things are connected together, but they're virtually never connected to the internet, because that would be probably the stupidest possible thing you could do. And maybe not the stupidest possible thing, but it would not be a good idea, right? Try to stay away from the superlatives here. So for somebody to take advantage of one of those things, they would have to get physical access. So they're going to have to go into a voting, a polling station, voting location. They're going to have to start walking up to these voting booths and take some physical. I mean, it's extremely unlikely that anybody could do that without being detected, and somebody calling the police, and et cetera. So is it a likely threat model for somebody to attack election machines, individual election machines? It's extremely unlikely. Personally, as a cybersecurity professional, the things that I would be concerned about from a voting security perspective are things like voter registration systems, right? So the voter registration system in a state, that's generally a centralized, or even in a precinct, that's a centralized system. And those things are certainly generally connected to the internet. It's just a database system connected to the internet, because that's how people interact with it. And for somebody to manipulate a voter registration system, that's first of all much more likely. That's something you could do from across the state or across the country or across the world. And if you manipulate who's able to vote where and when, then you're going to have a much more a much broader scale negative impact on voting than if you try to hack some individual, voting location, or even if you're able to manipulate the voter registration system, then that's where you start to cause mistrust in the whole system, and that's really what a more likely threat vector is. And then of course the other probably much more likely threat vector is something akin to the Russian meddling in the 2016 elections, using things like social media and bogus news and that kind of stuff. Why even try to hack a system when you can just create a bunch of puppet accounts, a bunch of sock puppets or troll accounts in Facebook or Twitter or whatever, social media of your choice, and then target people and try to get sort of polarize people, and that I think is a much bigger threat and probably certainly a better way to approach manipulating election systems at broad scale, and probably a lot more effective and a lot easier to deny, right? It's sometimes a direct hack, you can attribute it pretty easily back to the source, but some of these social media based attempts are hard to detect, harder to attribute, and pretty darn effective, I think, as we've seen in the recent past. And there are certainly countries who spend quite a bit of energy doing those kinds of attacks, and it's not a new thing, right? So these things have evolved from the days of using print media, printing press, up through just basic television news and print news, and the social media angle is simply a new spin on information operations and information warfare, something that nation states have been doing for millennia. Okay, so anyway, potential hack on voting systems, bit of news here. And then the other news is Oracle confirms China telecom internet traffic misdirections. So this is a news story that it looks like my screen switched here, so I'm going to just, oops. Again, sorry, I'm on my laptop. Okay, so this is a story about Oracle, the company Oracle, accusing China of misdirecting internet traffic. And so I need to pause this autoplay thing. Okay, so this is about, and I mentioned this, God, I hate these autoplay. So this is about something I mentioned in one of these workshops a couple of weeks ago. This is when countries who have control over internet core routers can manipulate routing algorithms on those core internet routers and cause internet backbone traffic to do strange things. And the accusation here is that, here's a nice picture of it. So this is a pretty simplistic picture, right? But this is, hopefully we can see it. I'll try to make it bigger on my screen. So this is, it's a network system in Los Angeles who is trying to send traffic to another system in Washington, D.C., right? So you obviously would expect that the internet would route this traffic through routers in the continental U.S. and get that traffic between Los Angeles and Washington, D.C. And I've mentioned previously, and we'll talk a little bit about it today, is that the internet is designed to route around failure. So if there was some natural disaster in Texas, for example, that caused core routers in Texas to lose power, and those core routers are no longer part of the internet for a temporary basis, then traffic that you might see routed through Texas to Washington, D.C. would automatically be routed through other core routers in the U.S. And that's just, again, that's the way the internet was designed, to route around failure. And so that's a good thing in general, but it's a bad thing in a sense that the routing algorithms that cause that to happen are vulnerable to people who potentially might misuse them. So if you sort of lie to the other, so these core routers, they all communicate with each other through a particular protocol called BGP, Border Gateway Protocol. So these routers send these BGP messages back and forth to each other all the time. And basically what those messages are saying is, hey, these are the routes that are available to me. And so they're advertising network routes, internet routes to each other. And the end result of all that is each one of these routers is going to compute the expected shortest path between two different locations in the internet. So so what normally you would expect to happen within core routers in the continental United States, for example, is they would all be communicating over these, using these BGP messages, and they would realize that the shortest network route between Los Angeles and Washington, D.C. is a path that's going to, it's almost always going to be core routers that are in the continental United States. Now, those pathways change over time, and they change actually fairly frequently. And the reason they change is not so much because of failure, right? So again, I said that these the internet is designed to route around failure. So sometimes when you have a node that fails, then the traffic's going to get routed around it. So this is not so much failure as it is load on the different legs of the network, right? So as network changes over time, over the duration of a day or a week or a month, the shortest path might be sort of clogged with too much network traffic, and then so what's going to happen is, again, the internet is going to naturally route around those sort of backed up pipes, and they're going to cause traffic to go on a pathway that's less congested. And so so the accusation here is that there was that China Telecom, which controls the border gateway protocol routers in the core routers in China, configured some routers so that they would essentially lie to these routers in other parts of the world and say, hey, we have a shortest path from Los Angeles to Washington, D.C., for example. And so what happens when you get that sort of bogus data sent over this BGP protocol is traffic, instead of being routed directly like you would expect it to be, gets routed here in this case all the way across the Pacific to China, then to another core router in China, and then back across the Pacific to Washington, D.C. Now, in terms of a user of the network, you wouldn't even notice that. I mean, you're going to get a slightly longer delay in your network traffic, but I mean, you're talking about milliseconds, right? So this traffic is traveling at roughly half the speed of light. And so you're really not going to notice the fact that the data traffic traversed the Pacific and went to China. So who cares? Well, who cares are the people who are communicating, because now your data, instead of being located within the continental United States, whatever data you're communicating is traveling over to China. And if that data is not properly encrypted, or if your encryption technology is not quite up to snuff, then it could be that the Chinese could intercept and eavesdrop on your communications. So that's the threat model, right? Is that your communications could be observed and manipulated. All right, so let me jump back to my slides here. And this is not a new thing. This is not a new thing. This has happened before, and here's an example of it happening before. And this is a news story from 2013, and this certainly wasn't even the first time that this happened. But this is an example of a core router in Reykjavik, Iceland, that was misconfigured, or either intentionally or accidentally. And so here you have the country of Iceland. Here you have Western Europe. Here you have the continental United States. And so here's an example of email traffic that should have traveled, that was between two computer users in the city of Denver, Colorado. And the traffic started in Denver, and an email was sent, and it went to a mail server in Dallas, and then that message went to another mail server in Kansas City, and then the recipient of the mail opened the mail, and so the email went from Kansas City back to Denver. Okay, so why did the email have to travel to Dallas and Kansas City for two users in Denver? Well, it just happens to be where their email servers were located. So, the way email works is it has to traverse through the email servers of the users of different email services, and so that's why the message normally would have traveled through that path. But because the core router in Reykjavik, Iceland was improperly configured, the message actually took this route, the red route. It went from Denver to Chicago to Ashburn, Virginia, to New York, to London, to Reykjavik, to Montreal, back to Chicago, back to New York, and then around to Dallas. Whoops, sorry about that. Around to Dallas, then to Kansas City, then to Denver. Okay, so not only is this extremely efficient, now your email traffic again is leaving the continental United States. It's going through foreign countries' networks, and anybody on that path could intercept the message and potentially review it, read it if it's not sufficiently encrypted. So, this is sort of a fundamental problem with some of these basic internet protocols. Again, this is something we may have mentioned before, but these things were designed to function efficiently and quickly, and they weren't designed to function securely, is the bottom line. These things were created in the 70s. We'll talk about some protocols that were created in the 70s, and they work really well, and they've continued to work for 40 years, 45 years actually, the TCP/IP protocol. But when they were designed, they were not designed to be secure. That just wasn't part of that wasn't part of the design requirement. They were designed to work, and so BGP is a great example of that. And so now, how do we take this protocol that, again, does its job very well, but there's this implicit assumption that the people who are configuring the core routers are gonna not improperly configure them, and it's a threat model that is not currently well covered, right? So now we can detect when some of these things are happening, but we can't necessarily prevent it from happening. Okay, enough about core routers and BGP. Today we're going to talk about network fundamentals, so very introductory discussion of networking. And again, this is a brand new lesson. It's going to be added to the Cyber Basics Networking module as the very first lesson. Hopefully it'll be there by the end of the week. Okay, so let me pull up my network fundamentals lesson. All right, here we go, network fundamentals. Learning objectives, and these come, largely they come directly from the Virginia Department of Ed Cybersecurity Fundamentals 6302 course under the CTE curriculum. And so here are some learning objectives. We're going to describe a network, describe wired versus cabled networks. We'll describe a wireless network, compare cabled and wired, and compare cabled/wired and wireless networks, compare networking conceptual models, and become familiar with network security devices. So let's dive in here. First thing we do, and again, this was an oversight in my previous courseware. Never really talked about what a network was at the sort of the high level, and so that's what a lot of this discussion is going to cover. Right. So what's a network? So network is a collection of computing devices that communicate digitally using wired or wireless connections. Pretty straightforward definition, I think. Collection of computing devices, and those can be all kinds of different computing devices. They used to be computers. You think of a network as being multiple computers connected together, and then you start adding in peripherals like printers and scanners and what have you. And then on top of that, nowadays we start throwing in things like smart speakers and various IoT devices. But in fact, these things are all computing devices, and they're all connected into a network. There are different types of networks depending on the size and scale of the group of communicating systems. And we'll take a look at some examples of these different types of networks. Smallest scale is what's referred to as a local area network, or LAN. This is a small group of systems, usually numbering in the tens to hundreds, that occupy a single office space, building, or home. So local area network is a small network connected by a network switch, and we'll take a look at those different networking devices here soon. Small group of systems, usually that occupy some relatively small physical area. And then the next level here is the wide area network, WAN. Wide area networks generally cover a larger geographic area, contain many LANs that comprise hundreds to thousands of systems. So wide area network is many, it's often many local area networks sort of connected together, and then you can have WANs that are of different scales, and you'll hear people talk about things like MANs or metropolitan area networks, right? So a MAN is a network that covers a particular metropolitan area, and that is just a type of a wide area network. And then the next level up here, and so these definitions are maybe not super detailed technical definitions, but I think they're sufficient to make a student, a high school student or a college student, sort of get a basic grasp of what these different terms mean. And I'm not going to try to get into specific technical definitions, because I think you can talk to 10 different network engineers about exactly how big is a LAN and exactly how big is a WAN, and they won't be able to agree. So these are relatively broad definitions. The internet, though, this is pretty clear. This term refers to large numbers of small networks connected together to form a larger network. And this term is most commonly used to refer to the global network of systems and devices that comprise the World Wide Web, as well as email and other services. So we all know what the internet is, and the capital I internet is just one example of an internet. So anytime you interconnect networks, then you have an internet. But the most obvious example is the worldwide internet that essentially connects countries around the world together, and it gives us access to sort of the global World Wide Web and email systems and all that kind of stuff. So just some basic definitions. So now we'll look at some examples of some of these different kinds of things. And I like this example because students should be, I would guess that students will be familiar with this kind of a network. They maybe just not sort of think of it in these terms. And this happens to be an example of a wireless network. And it's a home network, right? So if you think of a home network, get my mouse going here. So here, what is this? Does this let me draw stuff? Laser pointer, what does that do? Oh, look at that. Okay, here we go. I got a laser pointer. So here's a home network. Internet access is provided to the home by an internet service provider to the cable modem. In this case, it's a local cable company. So one way that many homes get their broadband internet access is through their cable company. And so in their home, they would have a cable modem. And the cable modem is connected by a wire into the wall. And this is a coaxial cable, just a general TV cable connection. Looks like a TV cable in most cases. And that's how your internet gets into your home network. And then in order to share that network signal with other devices in the home, then generally you have to connect it to a wireless access point. So here in this example, I have the cable modem connected with a wire. This would be a Cat5 cable wire to a wireless access point. Now, in some cases, ISPs are providing cable modems that have the wireless access point built in, right? So it's cable modem and wireless access point all in one. Something that you can do if you want. This is the setup that I use until I have a reason to use a different setup. So cable modem, Cat5 cable to a wireless access point. And then in the home, I have multiple different computer systems, printers, smart speakers, IoT devices, smartphones, tablets, Kindles, e-readers. I guess I'll be less platform specific and say e-readers, smart TVs, streaming media devices. There are all kinds of different streaming media devices by Amazon and Roku, and I don't know who else. There's probably a Google one. I know there's an Apple one. And so all these devices generally are going to connect wirelessly to your wireless access point. They're going to get an IP address within the home network, and then their traffic is going to get routed through the wireless access point to the cable modem and out to the internet. And this cable modem does this clever thing called, I'm sorry, not the cable modem, the wireless access point does this clever thing called network address translation. And I'm not going to get into the details of it today. We'll talk more about it later. But what this does is it converts the IP addresses of the various devices within your home network into a single IP address that you were issued by the ISP, right? So the ISP is going to give each customer a single internet protocol address, and we know that in order for a device to communicate over the internet, it needs to have its own IP address. So each one of these devices has to have its own IP address. And we use a technique called network address translation to essentially, the wireless access point is going to assign IP addresses, internet protocol addresses to each one of these different systems inside the home network. And then when the traffic goes from the device to the wireless access point, the wireless access point is going to swap that temporary or that internal IP address to the external IP address assigned by the internet service provider, and then that communication can happen out to the internet. And then when it comes back, the wireless access point is going to do the conversion the other way and send the traffic back to the individual device. And that is that really makes the wireless access point one of the best things that's happened to internet security in the last 20 years. And I throw that out once in a while, and lots of people don't sort of grasp why that's the case, but it has everything to do with network address translation. If you don't do network address translation, if each one of your internal systems were publicly routed all the way out to the internet, then hackers could hack on your individual systems all day long and try to penetrate them. And if you had a Windows computer that had a remote desktop protocol port open, for example, and it didn't have a great password on it, then some hacker could get access to your home computer, and that would be bad. What the wireless access point does is it prevents anybody out on the internet from even seeing your devices individually on your home network. All as they see is the wireless access point. So as long as wireless access points are kept secure by the vendors and by the owners, then you should be in good shape in terms of securing your home network. Unfortunately, there were some issues with vulnerabilities in wireless access points recently over the last year or so. Maybe we'll talk about those another time. But one thing I would encourage people to do who want to make sure that their home networks are secure is update the firmware on their wireless access point. And maybe I'll do a demo of that in a coming lecture, but it's fairly straightforward. Basically what you do is you get on your home computer, you connect directly to your wireless access point, usually through a web page. If you don't know how to do that, then you can Google the wireless access point model number and manufacturer and get instructions for how to connect to it. And then there's always a button on the home page. These days, there's always a button on the home page to update the firmware. Okay, so this is a local area network. Ethernet cable connects the cable modem to the wireless access point. I mentioned that already. Other devices in the home are connected to the wireless access point via wireless network connections. The WAP routes traffic from each device through the cable modem back out to the internet. So this gives each one of your network. So for example, your home computer, if you surf to a web page, what happens is there's a wireless connection between the computer and the wireless access point, and then that HTTP request, that GET request, it gets sent over the wired connection to the cable modem. From the cable modem out to the internet, gets routed to the device on the other end of the internet from which that web page is going to get served, and then the responding web page is going to get sent back to the cable modem, goes back to the wireless access point, and then gets transmitted wirelessly to the computer, and that web page comes up on your laptop. Okay, local area network. Everything on this picture is within the cable modem is the local area network. Some network components that are useful to make all these different kinds of networks function. are things like network interface cards. So here's a picture, here's a clip art of network interface card. If you've been around a while, you've probably seen some of these. These are the old ones that would plug into the motherboard on your old desktop computer. Nowadays, most network interface cards are going to be built into the motherboard of either a desktop or a laptop or your smartphone. So they used to be a thing that was 4 or 5 inches long by 2 or 3 inches wide and had a bunch of pins that would plug into the motherboard. Now the thing is probably the size of your fingernail on your little toe or smaller. But this network interface card connects a single computer to a network switch. And this example is a cabled network interface card. So NICs are part of computers and other connected systems and allow wired or wireless digital communications with other devices. And obviously there are different network interface cards for wired and wireless connections. So if you have a laptop that has a RJ45 port in it that you could plug a Cat5 cable into, that is going to have a wired network interface card built into it, and it's going to have a wireless network interface card to do Wi-Fi communications with a wireless access point. So all network connected devices have to have a wireless interface card, or that functionality has to be built into the motherboard. A switch connects multiple network devices inside a single local area network. Okay, so a switch, here's a clip art of a switch, and what you see on a switch is multiple switch ports on the right side of this thing. So this looks like it's a 24 port switch. And so this would allow you to connect 24 computers, in a wired network to each other, basically. So that would allow those 24 different computers to communicate with each other. And then there would be a cable that comes out of the switch to another switch or to a router, and that gets the traffic from those computers out to other network devices. But a single local area network is connected through one or more switches. And then a router routes network traffic between local area networks and wide area networks. So you have routers of varying sizes depending on the size of networks that they connect. And hopefully that makes sense. But if you imagine, if you have a router that's routing traffic between 2 office buildings, maybe each office building has 1,000 people, then that router is going to be of a certain size and bandwidth throughput. But if you have a core internet router that is routing traffic between many millions of people a day, then those routers are obviously going to be larger, have more functionality, more memory, more capacity. So routers run the gamut from relatively small and inexpensive in the hundreds of dollars up through hundreds of thousands of dollars for these large core routers in the internet. And so I mentioned these large core routers serve as the backbone of the internet. So if you ever heard the term internet backbone, that's these core internet routers owned by both government organizations and internet service providers like Verizon, AT&T, et cetera, et cetera. Okay, so these are basic network components. These are not all the different network components, but I think this is sufficient to make students sort of understand the basic things that make a network function. And so now that we know about some of the different network components, let's talk a little bit about wide area networks. And here in my example, I don't know, my drawing is not great, but so here we have multiple home networks. So let's imagine that each one of these looks something like this, right? So each one of these homes has a cable modem, and the cable modem is connected to a wireless access point, and then you have multiple individual devices inside the home network. So imagine that each one of these little home icons is one of those, and now the cable company is going to aggregate all these connections from these different home networks. And so this is a network switch, and this thing is, this isn't going to be like sitting out on the street somewhere. Obviously, this is going to happen in, probably back at the cable company. So the cables coming from all the homes are going to get aggregated in neighborhoods, and then there's going to be a higher bandwidth cable. It's going to get the traffic back to the cable company, but you'll have multiple homes in a neighborhood connected to a network switch. So individual home networks in a neighborhood are connected to a switch at the ISP, and then multiple neighborhoods can be connected together via network switches and routers. So you can have more of these neighborhoods connected over more switches, and there's this hierarchy of switches and routers that aggregate these networks together into larger networks. And then here's 2 of 2 of the wide area network. So now imagine that here you have an ISP. Let's say this is the cable company in Blacksburg, Virginia, for example, and that internet service provider, might serve 5,000 homes in the city of Blacksburg. And then you have ISP number 2. This might be the phone company who provides DSL service, and DSL is a different type of broadband internet provider, and so this might serve a couple of thousand homes. Then you might have another ISP that serves some other number of homes, and then these multiple wide area networks can be connected to, again, routed together, and then that router could be connected out to the internet. So many internet service providers can be connected into a WAN using routers. One or more routers are connected to internet core routers providing access to the wider internet. So this is just an example of how this could be set up. It may have no basis in truth, but it certainly different metropolitan areas are going to have their networking set up in different ways, but this is sort of a conceptual model of how this could be configured. Okay, so that's local area and wide area networks, and how different levels of networks are sort of connected together. Hopefully that makes some sort of sense. Next couple of slides are going to talk about wired versus wireless networks, and this is pretty straightforward from just a sort of a network. From if you just think of how the network is connected. Obviously, a wired network has a bunch of wires. So here I have that 24-port switch. Here I have a bunch of computers, and they're connected by wires to the 24-port switch. And then you have the printer that comes in, and then you have another. These systems could now all communicate with each other and with the printer. And then if they want to get connected to the internet, then there needs to be a wire out to something else that will get them to the internet. This particular picture does not show any connection to the internet. It simply shows a wired network that is connected to a wireless network. And so here's how that works. On the wireless network side, you have multiple devices that are connected wirelessly to wireless access, one or more wireless access points. And in a home network, you'll have a single wireless access point that serves that small location. So a wireless access point, the Wi-Fi protocol 802.11, IEEE 802.11 protocol is designed to support network connections of up to 100 meters in an outdoor area. So in perfect conditions, outdoor, no obstructions, it's supposed to be able to serve, to be able to connect to a device 100 meters away. Really, in practice, if you're inside a home with wires and all kinds of different interference from wireless devices and microwave ovens and whatever, you're going to get a lot less. The distance, the potential connection distance is a lot shorter, and in fact, even the different versions of the IEEE 802.11 protocol have different distances that they can connect. So in like a school, you're going to have multiple wireless access points, but those wireless access points are all going to be wired together, and they sort of provide this broad wireless network experience. And in this picture, I have a, so the point there is that every wireless access point has to have a wire connected to it to connect that wireless network to some other network. And in this picture, I have a wireless network that has 2 computers and a printer. These things are communicating wirelessly to the wireless access point, but the wireless access point alone, without this wired connection out to something else, is only going to allow these devices to communicate with each other. They're not going to be able to communicate out to the internet until you plug in a wire. And in this case, the wire connects this wireless network to this wired network. So now these systems can connect to this system. But you notice in my picture, there's no connection to the internet. So if you had a network like this, it wouldn't be a whole lot of use to you, because I guess this would allow everybody to print, but that's about it. You couldn't even send emails to each other in this network, because an email, unless one of these systems was an email server. But this is just a simple picture of a wired network and a wireless network. Probably too much explanation for it. So let's look at some pros and cons. So the green plus obviously are pros, and the red minuses are cons. Pros of a wired network: higher bandwidth, faster upload download speeds. So you can just push more data through a wire. And actually, wireless networks are getting closer and closer to the maximum speed of wired networks. But if you're using fiber optics, for example, I guess fiber optics. I guess you'd sort of consider fiber optics. Obviously, is not a wire, but I think you would put a fiber optic network connection under the umbrella of a wired network. You can push huge amounts of data through a fiber optic link, way more than you could push through a wireless link. So in general, wired networks provide higher bandwidth, and that gives you, so when I say higher bandwidth, that means faster upload and download speed. So if you're uploading and downloading movies over Netflix or whatever, you're going to do better with wires. And wired networks are not subject to interference by other wireless devices like phones and radios and microwave ovens and other things that emit electromagnetic spectrum that is going to cause the wireless network to potentially behave in a non-optimal way. No problems with that stuff in a wired network. The difficulties with a wired network are, number one, cost of installation is high due to routing of cables and potentially additional network devices, right? So there was a time after we had ISPs providing service to homes, before we had wireless access points, where and I remember having this issue back in the 90s. I was able to get my home connected to the internet, but I had no way to connect my individual home systems that were in different rooms together. They essentially were in the same room, and I could run a network hub and plug in those different computers. But in order to make connections between different systems in different rooms, then of course, if I were to try to set that up in my home before wireless access became a common thing, it would have been very difficult. In fact, there was a time period when homes were being outfitted with Cat 5 throughout the home, right? So right now you get, your home is generally wired for power and for telephone and maybe cable. And again, there was a time when people's homes were being wired for Cat 5 cables so that they could plug in network devices at various rooms in the home. And I guess some builders may still do that, but less need for that these days. Wired networks are less flexible, right? So if you want to change the network, then there's work involved. You might have to cut new network cables. There's all kinds of problems with even moving a single computer from one room to another. And then generally they're more costly to maintain and troubleshoot. Again, because now you have these wires, and you might have a wire that has a bad connection in a wall. Rat chewed through something. You have the end connectors on the wires that are notorious for getting damaged over time and not functioning properly. So, and then if you're gonna rejigger the network, then you got to rerun the cables, and so it's generally more costly to maintain and troubleshoot. Okay, so now if we look at the wireless network, you just sort of take all those things and you turn them on their head, right? So wireless networks are much cheaper and easier to install. You can network 100 devices together, no problem, if you just get a couple of wireless access points and put them in a place, and no reason to run cable or do any of that stuff. Generally cheaper to maintain for similar reasons. Extremely flexible, right? Devices can leave and join the network throughout the day. Imagine a situation where you had a college where students, when they brought their laptop into the classroom, they had to plug into the network, every time. It was just, of course, we're sort of spoiled by the fact that you can at Virginia Tech, you can walk anywhere and open your laptop and you're on the network sort of automatically and immediately. And with things like wireless infrastructure like edge roam or authentication infrastructures like edge roam. I can go to a different college campus in the U.S. or even some in Europe, and I don't have to do anything special to get on the network. I'm just on. So extremely flexible. Generally lower bandwidth. Again, these wireless network protocols are getting more efficient all the time, and so maybe the bandwidth will become. It almost doesn't matter. I mean, you get such good bandwidth on most wireless connections that in terms of connecting individual systems to the network, bandwidth is not an issue. But if you have a whole bunch of systems and you want to connect a whole bunch of systems to the internet or to a whole bunch of other systems, that's when the bandwidth becomes an issue, and you might have to have wires in there somewhere. And then there's subject interference by wireless devices, microwaves, anything that emits EM radiation is going to potentially interfere with your wireless network. Okay. So now let's dive into the internet. It looks like from my watch I have about 7 minutes to do this. So the internet started in the 1960s when a handful of universities in California and Utah were connected as part of a project sponsored by the Defense Advanced Research and Development Agency, DARPA. And actually at that time it was not DARPA, it was ARPA. So the defense was added later. I should fix this slide. The Advanced Research and Development Agency, ARPA, was a research agency that did research that created the internet. Network quickly expanded to include the entire US as well as countries around the world, mostly used for electronic communication. So basically email, bulletin board systems between university students, faculty, research center scientists, government agencies, right? So back in the 60s, 70s, 80s, people generally didn't hear the internet, didn't know what the internet was. It wasn't until the 1990s, with the advent of the World Wide Web by a smart guy named Tim Berners-Lee. He invented the World Wide Web, and that became the thing that made the internet useful to the general population, right? So before that, the internet was used for email between different people. It's kind of an interesting, useful application, but probably not useful enough for somebody to pay to get their home connected to the internet so they could send emails to people, right? But the World Wide Web was of sufficient utility that's what sort of caused the explosion in broadband usage and really caused the internet to explode. And then the last bullet here, increased access to high-speed networking has caused the internet to grow from the dozens of devices originally connected to billions of computers, phones, cars, industrial control systems, Internet of Things devices, etc. Right? So billions of systems on the internet. So quick history lesson, ARPANET back in December 1969. This is when this thing was first created, again, funded by ARPA. And there were 3 colleges in California and 1 college in Utah. And they had, each one of these locations had smaller scale networks, right? They all had these small local area networks, a couple of large computers. Back then computers filled a room instead of fitting in your pocket. But they were able to communicate between computer systems in their at their location. But what the internet provided was the ability to connect devices over long distances. You couldn't use these same network protocols because there was timing that was very specific, and the time that it took for packets to traverse long distances caused these, the protocols that would make these small networks function. It just wouldn't work at all. And, everybody had their own sort of proprietary protocols that they were using to have their devices communicate. The internet sort of made all that. It sort of made it all general, and everybody started to use the same protocols. So this is what the ARPANET looked like in 1969 when it first started. Again, 4 colleges connected in this grand experiment that was the internet. Then in the 1970s, a couple of smart guys, Vint Cerf, Bob Kahn, they were both working for ARPA at the time. They're both computer science. Well, so Vint Cerf is a computer science PhD. Bob Kahn was an electrical engineering PhD, and they developed they led the team that developed the TCP/IP protocol, published a paper in 1973, describing those two protocols that work hand in hand to make the internet function. And from there, it's sort of everything went off the rails, right? So now this was by 1982. So 9 years later, we had locations all across the US. So each one of these dots represents not a single device, but many devices in a local area network connected via the internet. You had these satellite connections that went to London and went to Hawaii. Pretty quick scaling of the internet. And again, this is before the World Wide Web. This is still just research agencies and colleges communicating over email. And then this is a map of the internet today, and it shows devices. So it shows transatlantic cables. So these lines over the oceans are transatlantic cables. So look at all these cables across the world that connect folks to the internet. And then within the continents, you have these, you can sort of identify where the core routers are by these, by these sort of more congested dots. And then, it's pretty clear to see where the population centers are, right? Things are pretty sparse out here in the Western United States, definitely more dense in the East. Coastlines are generally more heavily populated. So lots more internet on the coastal areas. India, very, very densely populated. China, lots of cell phone use, and et cetera. But this is kind of a cool map that just tries to represent the scale of what the internet is now. And obviously now it's millions of smaller networks connecting billions of devices across the world. So quick overview now. This is the last couple of slides. I wanted to switch gears and talk about network security devices, and there'll be more discussion of network security devices later on. So two basic network security devices are listed here. One of them is a firewall. Firewall is a network device that blocks network traffic based on IP address, ports, and protocols. So it's there are different, and we're going to talk a lot more about IP addresses and ports and protocols later on. I just want to get these definitions out and talk a little bit about how they function. Firewalls can be network-based. So if they're network-based, they're blocking traffic coming into the network. And remember, you have a network connecting multiple systems, and if you put the firewall at the edge of the network before the traffic gets into the network, then you can block traffic and attempt to protect all those internal systems from somebody trying to compromise them from outside. Firewalls can also be host-based. So on a host-based firewall, you block traffic on the endpoint. So now you're not blocking traffic at the edge of the network, you're blocking traffic as it enters the endpoint computer. And then many organizations use both of these techniques, right? So you'll have a network firewall on the edge of the network. You'll have host-based firewalls on each of the hosts in the network. And then this is something that we refer to as defense in depth. And we talked about defense in depth in an earlier workshop. So, if you do both, then your potential to secure your systems is higher. Okay, then another sort of basic sort of network security device is an intrusion detection system, and that is just what it sounds like. It's a network device that monitors network traffic and alerts security analysts of possible intrusion attempts into the network. So the early IDS systems were very rule-based. So we had these known exploits against known vulnerabilities, and the developers of these IDS systems would basically make rules. They would say that if a network packet has these specific characteristics, then it's this attempted malicious packet, and you're going to alert a security analyst. So rule-based intrusion detection system detects previously discovered intrusion attempts. I'm going to fix this slide too, for which, again, I just created these this morning, so I'll fix a couple of typos in these slides. Detects previously discovered exploits for which rules have been created. And then you have this notion of an anomaly-based intrusion detection system. And what this tries to do is identify what routine network traffic should look like, and then it flags what is called anomalous network behavior, and that anomalous network behavior is suspected malicious traffic, right? And I say suspected malicious because you can imagine that if you are trying to characterize normal behavior and then identify what's not normal, there's lots of potential for what we call false positives, or misidentifying non-malicious traffic as malicious traffic. And that's why generally they're set up in this IDS configuration. So instead of automatically blocking the traffic, you alert a security analyst who can take action. And that's because you have this potential high rate of false positives. You don't want to block a bunch of good traffic when it shouldn't be blocked. And intrusion detection systems can be network-based or host-based, just like firewalls. Okay, so here's a quick picture. And so think of this picture as getting closer and closer to the core of your organization's network. So let's say this is your high school network, right? So this picture represents the high school network. So out here is the big bad internet, and then the top picture here shows how a firewall sits on the network. So you have the big bad internet, and then you have an edge router. So this router connects the school to the internet. And then you have a network firewall. And so this network firewall is going to block traffic on specific IP addresses, ports, and protocols that should be blocked, right? So this is very rule-based. Network firewall is configured to block specific ports and protocols. And then the expectation is that the network traffic coming in from the firewall is much cleaner and doesn't have a bunch of malicious hacking attempts and that kind of stuff. So network firewalls have been around for 15 or 20 years, and they do a lot to sort of clean up traffic as it comes into a network. And people sort of argue the usefulness of a firewall. I mean, they certainly do something productive. They may not be as the panacea that some people sort of expect them to be. But anyway, you notice that the firewall sits in line, right? So this is going to block traffic that is not supposed to get through. And then the bottom picture is a similar network map. So here you have the internet, and then you have the internal, for example, high school network. Intrusion detection systems usually, and I put usually here, and because no superlatives, I'm going to not say that they always are configured this way. In fact, they're not always configured this way. They usually observe but don't block traffic. So what you do is you essentially have a tap on the network that is able to take a copy of all the network traffic and send it to the intrusion detection system. The intrusion detection system is going to function either in a rule-based way or an anomaly-based way, or both. And then when it sees a suspected intrusion, it's going to send an alert to a security analyst, and then the security analyst is going to go back and inspect the device or inspect the network traffic and see if there was an intrusion or not. Again, you don't block the traffic because there is lots of potential for false positives. However, in some cases where you want to be way more conservative, you can put an intrusion detection system in line like a firewall. In that case, you refer to it as a intrusion prevention system, and you block potentially malicious traffic. Generally, you still send an alert to a security analyst, because the security analyst might need to go back and say, hey, that was a false positive. I need to reconfigure the IPS to not prevent that kind of traffic. Okay, so quick overview of basic network security devices, network firewall, and an intrusion detection system. And we can talk a lot more about those two different kinds of devices and other network security devices later on. Just wanted to introduce them here. Okay, so that's it. I'm going to stop. Once again, I thought I was going to be short, and it looks like I'm over by a few minutes, so I apologize for that. Hopefully people who were listening to the recording fast-forwarded through a lot of my rambling about BGP, but thanks for joining us, and this session will get posted, I imagine, by the end of the week and available more broadly. So thanks. See ya.